On the last video, we were doing some indeterminate limits, meaning the limit comes out to be 0 over 0. And I said to do some algebra. Okay, there are some kind of special cases here. So here I have the limit as x approaches 4 of absolute value of x minus 4 over x minus 4, which clearly if you plug in 4 gives you 0 over 0. Okay, so this particular one, if you get a limit with an absolute value that's indeterminate, it's probably a good idea to look at the two one-sided limits on this one. Now recall for absolute value, when is it okay to just remove an absolute value? If the stuff inside is already positive, then you can just pull off the absolute value, right? Absolute value of stuff is just equal to stuff if my stuff is positive. But if what's inside is negative, then if I remove the absolute value, I have to add another negative to make it correct. For example, right, if the absolute value of -7, if I just remove the absolute value, is not true, but if I throw in another negative, then it is true, right? That equals +7. So with that in mind, there was my example there. Okay, if I look at the two one-sided limits, if x approaches 4 from the positive side, remember that means I'm using numbers a little bit bigger than 4, in which case x minus 4 would be positive. So in that case, I can just remove the absolute value and I get x minus 4 over x minus 4. Those cancel out, I get 1. But if x approaches 4 from the left side, so if you're using a number like 3.9 or something, this would come out to be negative. So as we saw, you would then have to drop the absolute value with an extra negative sign. Those cancel out and I get -1. And so then this goes back to what we talked about, is that if you get two different values for your one-sided limits, then the overall limit does not exist. Graphically, this is kind of an interesting graph that you probably will see multiple times in calculus. The graph of the absolute value of x minus 4 over x minus 4 actually is just two horizontal lines. It turns out that any number you plug in bigger than 4, you're always going to get +1. And any number you plug in that's less than 4, you'll always get -1. But of course, it is undefined at 4 because you're dividing by 0. So they would have open circles there. Okay. And just a reminder from what we did on the last video, we talked about that normally if you get a 0 over 0 limit, we've seen that you can handle it by factoring, by using the conjugate, finding a common denominator, etc. These are algebra skills. So if you get a 0 over 0 limit, your first line of attack is to do some algebra. Okay. Now there are some special cases, like we said with this absolute value one. That being said, there are some times when algebra is not going to help. So if we look at this limit, x approaches 0, 10 to the x minus 1 over x gives you 0 over 0, which is indeterminate, okay? But there's no algebraic way, I don't know any way to factor, do a conjugate, to rewrite that. So later on in the quarter, we're going to learn another method to evaluate this limit. But right now at this point, when this happens, we're kind of stuck. And so what you can do, and I think it's important to acknowledge that you can answer limits numerically with a calculator. So if you pulled a calculator out and you plugged in, you took some x values to the left of 0. Notice they're getting successively closer to 0 from the left side, and my positive values are getting successively closer to 0 from the right side. And if I evaluate my function, 10 to the x minus 1 over x at these numbers, what you notice is that my trend, as we get close to 0 from the left, it looks like my values are getting closer to about this I think is 2.299. Okay, about 2.3. And if I plug in values, positive values getting closer to 3, you can see that my trend is heading towards also 2.3. So it's reasonable to conclude then that that limit, the overall limit, is about 2.3. And that is correct. Okay. Again, later on in the course, we will find a way to get the exact answer, which actually is going to end up being ln of 10 using something we call L'Hopital's rule. That involves derivatives, which we're not there yet. We're going to learn that later on. So for now, we're going to have to approximate these limits using a calculator. Okay. Now, when you use a calculator, you do have to be careful. Okay. Oops, let me slide that down. There we go. When you use a calculator to approximate a limit, you do want to be a little bit careful. Because it's important. A lot of people would say, if I go back to my last example, why don't you just pick, why is it important to pick these values? Why don't you just pick 0.001, and realize that's about 2.3 and then just say that's the limit, okay? It is important that you check successively closer x values because you want to make sure that your values are trending in that direction towards a certain number. Otherwise, you could get tricked. Okay, let's look at this limit, x approaching 0 from the positive side, sine of 1 over x. If you plug in 0, this time you get sine of 1 over 0, which is not even, that's not 0 over 0. What is that? How do I make sense of that, right? So let's look at, we'll make a table, and I'm going to hide this for the moment. Well, I guess I'll just, okay, show it. So, but notice what happens. If we had said, well, let's just take the closest value to 0 as we can, so why don't we just plug in 0.001? If you plug that into a calculator, and by the way, if you're using a trig function, remember that when you use these values, these are in radians, okay? In calculus, we don't work with degrees very much, okay? You should be using radians. If you plug that into sine of 1 over x, you're going to get negative 0.31. So it might be tempting to say, oh, the limit must be about negative 0.31. But if you look at some values getting successively closer to 0, look what happens. We get negative 0.54, negative 0.51. There looks like a trend there. And then all of a sudden it jumps up to positive 0.87 and then back to negative 0.31. Clearly, there's no trend apparent here. And in fact, that limit does not exist, okay? If you had just picked one value and put that down as your answer, it would be wrong. In fact, what's going on with this graph, if you do graph it on a graphing calculator, you'll see that what happens, it's a sine graph, so it does have a lot of oscillations, but as this graph gets closer to 0, there ends up being an infinite number of oscillations up and down between 1 and negative 1. And so what was happening for us is we were picking values close to 0, and we got a negative value, and then occasionally we got a positive value because we were up on one of these curves here and then back down to negative. So the limit doesn't exist. It oscillates infinitely. And again, just a note, word of caution, if we had just picked one x value close to 0, we might have been tricked into thinking that the limit existed, and it really doesn't. All right. Next example, I think this is my last example for this video. So this time I have x squared times sine of 1 over x, which if I plug in 0, gives me 0 times, again, I get that weird sine of 1 over 0, and I'm like, what does that mean, right? How do I make any sense out of that? Now this particular one we're going to take, I could definitely use a calculator, okay? We could use a table and approximate. We would have to pick values to the left of 0 and to the right of 0, and that would work, okay? But there is a way to do this without a calculator. And that's what we're going to do is by noticing that the sine function is always between -1 and 1. If anybody gives you an angle and has you find the sine of it, we're guaranteed to find an answer between 1 and -1, because that's how the graph of sine looks. So the sine of anything, including 1 over x, which is part of my limit, is guaranteed to be between 1 and -1. If I take that inequality and multiply both sides by x squared, now I have x squared sine of 1 over x is between -x squared and +x squared. And if I now take the limit as x approaches 0, this was the limit we were trying to find, and take the limit of both sides, what do we learn here is that the left limit, if you plug in 0, that goes to 0. The right limit goes to 0. So no matter what, this limit doesn't have a choice. It's trapped between 0 and 0, so this limit has to be 0, right? It has to be 0. And this is called, there's two names for it. It's often called the Sandwich Theorem or the Squeeze Theorem. And it kind of makes sense. We've sandwiched our limit between two other limits, which both happen to equal 0, which gave our limit no choice but to equal 0. So the Sandwich Theorem is another skill. This is talked about in our book. This is probably not the last time you'll see this. We'll do some examples with that. And finally, what that second line of our proof is telling us right here, what that's also telling us graphically, this is our function. Graphically, it's saying that our function always falls between the graph of y equals -x squared and y equals +x squared. So if you can imagine, and you can confirm this with a graphing calculator, here's y equals x squared, here's y equals -x squared. What this graph is going to look like, it does have a sine in it, so it is going to oscillate, but it's always stuck between these two parabolas. So as we get closer to 0, it's kind of, see how it's getting sandwiched between the two parabolas, right? Same thing on the left side. And so you can tell why that limit has to be 0, because it's the two parabolas get closer to 0, right, as you get towards the origin. So kind of an interesting graph. Okay, that's it for this video.